go ahead and start there. I'm going to go ahead and share my screen with you, but I would also encourage you to have up your code as well as the question itself as well. All right, so let's go ahead and share my screen with all of you. Okay, so notice, I guess the first thing that you may have noticed about this problem that's different than the previous 2 or 3 that we've looked at is that even though this question fits the category of methods and control structures, which if you took a look at the chief reader report, as I instructed you to do so, it says it right there. The topic for this question is methods and control structure. So what's different about this question is that it only involves the use of one class, whereas at least the previous 2 involved the use of 2 classes, and that second class was a list, involved some type of array list object. So that's not the case here. We're not doing anything with lists or array lists. We just have one class. However, we're dealing with a method in this hop distance that is somewhat abstract. So if we take a look at the comment just above the hop distance method, we can read the comment that says it returns an integer representing the distance in inches to be moved when the frog hops. Now, I wish, just like you wish, it had been more explicit. It had said more about specifically how many inches, what is the possible range that exists for this hop distance method? We get a little bit of a better answer to that question by looking at the table below, which provides 5 examples of what the possible outcome might look like given a frog simulation object with the parameters 24 and 5. 24, of course, being the goal distance, 5 representing the max number of hops. So each one of these examples represents an example of a possible outcome by running the simulation and what each individual hop distance would produce on any given hop. So if we just take a look at the table and scan through, we can see that in the first example, we have integers in the single digits, so 5, 7, -2, 8, and 6. The second one, 6, 7, 6, 6, 6, -6, 31, which is a little bit of an outlier there. But what we can really assess from this table is that the largest integer that was produced was 31, and the smallest integer that was produced was -8. So when you created or when you wrote the hop distance method, and again, you were not required to answer, or rather write the implementation for the hop distance method to successfully answer part A and B, but you were required to do it if you were going to write the full class and test everything out in some type of IDE. So answers may vary depending on what you thought was an appropriate range of values for the hop distance. But again, it actually doesn't really matter. All you have to know in order to successfully complete this problem is that the hop distance method produces some random integer, positive or negative. We don't know. We don't know, and it's actually not that important. But to make this whole thing work in a similar manner to the examples that are given, I used the math.random function, which had to be used, times 31, which would produce then a random number between 0 and 30, okay? Because remember, we're casting as an int. If any of you read Victor's comment, he explained it very nicely. So thank you, Vic. Math.random on its own produces some random number, that number being a double, from 0.0 up to but not including 1. So in theory, you could have 0.999 repeating up to the 14th or 15th decimal place, okay? So math.random times 31 will produce some random number between 0 and 30, given that we've cast it as an integer, okay? And then I subtracted 10 from that so that the range now is from -10 to +20, okay? And even though in the example that was given in the table, we can see that there was a value of 31 that was produced. So if I want to, I can make this, a little bit larger to fit that, and I can make this 41 instead of 31. So let's just hit the pause button real quick and see if anybody has any questions with regards to this hop distance method, which of course was not required in order to successfully answer parts A and B in the context of, you actually writing a solution on the day of the AP exam. But if you are trying to utilize some type of IDE and you really want to test out your code and you really want to see if everything works, then you're going to have to fill in the blanks in certain spaces. And this is one of them where they give you a method, they tell you how it works, but they don't show you the implementation for it, okay? So for those of you that were having some issues with the hop distance method, does that clarify your questions? What do you mean you did a coin flip method to determine if it was positive or negative, Matthew? I see. Got it. Got it. Okay. So again, there was really no one specific, I should say, there's always a wrong answer, but there were many right answers to writing the implementation for the hop distance method, okay? As long as you incorporated the use of the math.random function and you casted that result as an integer, because of course the method returns an integer, then really anything that you put would be a valid implementation, okay? However, if you want the simulation to run in a similar fashion to the examples that are given in the actual problem, you might want to have something that's similar to what I have here. So either 41 or 31, something in that range. And we can stick with 41 for now. But what you'll see is that in part B, I was getting a success rate of roughly, 70%. And I was trying to get it somewhat closer to 50%, or maybe just above 50% for the proportion. That was the method for part B. Okay. All right then. So we'll just go through then, starting then from top to bottom. We have public class frog simulation, the class declaration. We have the two private instance variables that are associated with a frog simulation object, the goal distance, so the distance we are trying to achieve in the maximum number of hops. So we have a goal distance in mind, and we have to achieve that goal distance in the max number of hops given, or fewer than that number, okay? So when we create a frog simulation, we give the frog simulation a distance, which is any valid, I believe, positive integer. That would have been, let's just double check that. So constructs a frog simulation, yes, precondition. Distance is greater than 0 and num hops is greater than 0. Okay, so you don't have to work when they tell you that, so that when you're writing the implementation for part A, you don't have to worry about like, oh well, what if somebody tries to put in a negative distance or use a negative number of hops, neither of which really make any sense. Well, we're told that the precondition is that distance and num hops are greater than 0, so we don't have to account for those things in our solution. And by account for them in our solution, I mean we don't have to account for them in the implementation that we're going to write. Okay, so it's sort of like, hey user, just know that you're not allowed to use any number less than 0 for your distance and your num hops. Okay. All right, so just a standard constructor, we're passing those two parameters, distance and num hops, over to our private instance variables. And we have the hop distance method, which we just spoke about, okay? Which brings us to part A. So part A asks us to complete the simulate method, all right? And the simulate method, it says, simulates a frog attempting to reach the goal as described in part A. Returns true if the frog successfully reached or passed the goal, that's the goal distance, during the simulation, and false otherwise. So I believe the solutions that are provided by the AP College Board, I believe it used a for loop. I happen to use a while loop in my solution, and we can take a look at the differences between the two. So again, this is a great point to illustrate. There's many right answers. There's always a wrong answer, but there are many ways to earn full credit. So I've introduced here two variables. One, current distance, which in the solution provided by the AP College Board, they call it position. So whether you use POS for position or current distance, they all mean the same thing in the context of this problem. So I'm assigning that to 0, which is our starting point. Hops, which represents how many hops we've taken throughout the simulation, okay? And in the solution provided by the College Board, they actually didn't introduce this variable at all, and you'll see when we examine the for loop alternative why that is. So while the current distance is greater than or equal to 0, now remember, the current distance can never be, and when I say can never be negative, if it becomes negative, then you stop what you're doing right then and there and you return false. So if this evaluates to false at any point, we'll exit the loop and we will return false. Okay, and we can see that right here. Now we have a complex Boolean here in our while loop header. So current distance is greater than or equal to 0. And as long as the hops are less than or equal to the max hops, then we're going to continue to run through the simulation and accumulate additional hops. So notice here that I've now reassigned my current distance to whatever the previous current distance was, plus hop distance. And again, we know the hop distance produces an integer. It returns an integer. Well, current distance represents an integer. So by adding these two things together, we get a new integer value that will be stored and updated in the current distance variable. Now, after we've updated the current distance, we want to increment the number of hops that have been taken. So hops plus plus. And we want these two things to happen so long as these conditions are true. Now we have a conditional statement that's going to determine whether or not we've met our goal distance. So if the current distance, which we could meet after 1 hop, okay? We could meet it after 2 hops, 3 hops, 4 hops. It just depends on what your max number of hops is and whatever integer is produced by your hop distance method. So if the current distance at any point exceeds or is equal to the goal distance, then you're going to return true. And remember, when you use the keyword return in the body of the method, and I should say really like in the body of a loop, it acts in a similar manner to the break keyword. So returning true means that at that moment, we're going to stop what we're doing, return the value of true, and we will no longer continue to execute this simulate method, okay? Well, let's just assume that the current distance is not greater than or equal to the goal distance. Then we will come up, test our while loop header, and so long as the current distance is not negative and the hops is still less than or equal to the max, the max hops, then we will continue to run the simulation. Okay, we'll continue to run the simulation. And I'm just now realizing that this hops is less than or equal to, I believe should just be less than, because let's say the hops was 5 and the max hops was 5. We would get to run the simulation an additional time, increase the hops to 6, and could potentially get the current distance greater than or equal to the goal distance. So we want to, I'm going to change that to just less than, okay? So, no, wait a minute. It should be less than or equal to. No, it shouldn't. Sorry, because if it's 4, if hops is 4, which is less than or equal to 5, which is less than 5, we will then get to run that hop distance a 5th time, increasing the hops then to 5, and then so on and so forth. So sorry, I apologize for that. It should have just been hops is less than max hops. So that error is now cleaned up. And if we go to the main method, we can check out, I created 5 frog simulation objects, just naming a variable sim1 through sim5, using the same parameters each time. Now, the reason I did this is because if we actually take a look at the problem, the table that's provided to us, it says, look, here's a frog simulation object. If you were to run a simulation, here are some possible, and it says it right here, the table shows some possible outcomes of calling the simulate method. So, and Tanmim, this may or may not answer your question or hit on the point that you brought up earlier about 20 minutes ago, is that you're going to get a different answer every time, just as you should. So each one of these is a different frog simulation object. So I'm now able to say system.out_print sim1.simulate, sim2.simulate, and so on and so forth. So just because they have the same parameters for each object doesn't mean that the outcome is going to be the same each time. Remember, it's a simulation, and the simulation is dependent upon the hop distance method, which is dependent upon producing a random integer, hence random, okay? So if we go ahead and run this, the sim1.simulate 1 through 5, given the same parameters of a goal distance of 24 and a max hops of 5, we get, just give it a second. Okay, we got true, 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 false. So 4 trues and 1 false. And we got the success rate of 69% or 0.69. Go ahead and run it again. It's always important to run it, especially when you're dealing with a simulation, you know, somewhere between 5 and 10 times. Notice how this time we got false, true, 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 true. I'll keep running it just to get a variety of answers. Make sure I'm getting a variety of answers. False, true, true, false, true. That's excellent. Okay. True, true, false, true, true. All right, we'll run it once more. and now we've gotten true, false, false, true, false. So I think in the 5 or 6 times I just ran the simulation, we got unique results each and every time, okay? Now, you might be wondering, even if you've done all this, how can I be sure that my method is working and satisfying all of the conditions that are stated by the problem? So it says right here in part A, the frog hops until one of the following conditions becomes true. So the frog has reached or passed the goal, its goal distance. The frog has reached a negative position, or the frog has taken the maximum number of hops without reaching the goal. All of which is illustrated in this set of code here, okay? Now, I'm not going to formally include this in my solution, but to double check that my simulation is working the way it's supposed to, I included, and I just uncommented that line out, in my while loop, I wrote a line of code, system.out_print cur distance, and then concatenated that with a space so that it'll print all of the, it's not going to print out these numbers here, okay? It's not going to print out the actual hop distance each time, but it is going to do something equally valuable. It's going to print out the position or the current distance that the frog is at that moment in time. So what we will be able to reassure ourselves of is whether or not that given a negative hop, not a negative hop, but a negative total distance or position, that it stops and automatically returns false, because that's very important, okay? Not that if it has a negative hop at any point, it's that the negative distance, total distance, is negative, then you stop and automatically return false. And we can confirm this by looking at the table. So notice here in example 1, the frog hopped a distance of 5 inches, then 7 inches, so its total would be 12, then -2, so its total would be 10. We have to take that 2 away from the 12. Then it hopped 8 and 6, achieving the final position of 24 in the maximum number of hops, which was 5. So just because it had a negative hop doesn't mean you automatically return false. You only automatically return false if, we can observe this in example 4, it hopped 4 inches, then 2 inches, then -8 inches. Now, 4 plus 2 is 6. 6 plus -8 is -2. So if the frog at any point has a negative total distance, then you stop what you're doing and return false, okay? So let's check this out. And by printing the current distance, we'll have a little bit more insight as to whether or not our simulate method is working correctly, okay? So I'm going to go ahead and rerun it. Okay, that is not what I was anticipating. Oh, it's because I had the run simulations going on here as well. Okay, I'm going to comment out that line there. So let's just get rid of that for a moment. Okay, there we go. So in simulation 1, it achieved a hop distance of 21. Now, it's not saying that it jumped 21 inches and then jumped 12 inches. It's saying it jumped 21 inches and then it jumped -9 inches so that its current distance was 12. Then it jumped 30 inches, exceeding the goal of 24, so it returned true. Now, it just so happens that in this simulation, they all return true. And when something like that happens, you should be weary of, okay, did I make a mistake? If it's always returning true and it should be returning true sometimes and false sometimes, well, guess what? It is a simulation. And just as you would with flipping a fair coin, everybody knows, of course, that if we flipped a coin, heads, and it has heads and tails and it's a fair coin, that the theoretical probability of getting heads and tails is 50%. 50% for tails, 50% for heads. Heads, whatever, they're equal, okay? Now, if I only flip the coin 5 times, it's certainly possible that I could get heads 5 times in a row. That doesn't mean that the probability of getting heads is 100%. That just simply means that my experimental probability happens to be 100% for heads, given a very small sample size. So one of the things that you may recall from probability, for those of you that are taking Algebra 2, is that as the number of trials increases, right, the law of large numbers, as the number of trials increases, the experimental probability and the theoretical probability, they get closer and closer together, okay? Well, just as that's true with flipping a coin, it's true with our simulation. So the fact that we got 5 trues here doesn't necessarily mean that we have an error in our code, and we established that by running the simulation 6 or so times previously. So let's just run it again. And notice how we've got totally different results here. So this is terrific, okay? This is exactly what we were looking for to confirm whether or not our solution for part A works. So notice that right off the bat, on our first hop in the first simulation, it hopped 9 inches backwards, okay? So it stopped immediately and returned false, okay? That's excellent. And then we hopped 23 inches in the second simulation. Then we hopped another 3 inches, giving us the goal distance of 26, so we returned true. This one, we got it on the first jump. This one, we got nearly there, took another jump, so true. Now, this last one is interesting. So it looks like we hopped in place, and I don't believe the hop distance method says anything about not including the number 0 as a possible distance. So it hopped in place again, and then it hopped 3 inches backward, yielding a result of false, okay? So that right there sums up everything we need to know for part A. I'm going to go ahead and comment out line 29. Would anybody like to see sort of the side-by-side comparison of the while loop that I used to the for loop that was used by the instructions? Okay. So just give me a second. Okay, just a second. Okay, so let's take a look at the solution that they provide. Notice that they only introduce one variable called position. This is comparable to my current distance, okay, Kerr distance. So my Kerr distance is equivalent to their position. Now, one thing I'd like you to notice is that they don't have this hops variable initialized before the loop. Now, that is because I'm using a while loop and they're using a for loop. One of the things we remember from using for loops and while loops, and of course, we remember this more so from when we are looping through a data structure like an array or a list, because with those, we tend to have a variable, an index variable, okay, that refers to the index of a specific element. We know, of course, that with a while loop, we have to declare and initialize the index variable before the while loop, whereas in the for loop, we do it inside of the header. So notice I'm referencing this hops variable in the header of my while loop right here. So my condition is while Kerr distance is greater than or equal to 0 and hops is less than max hops, whereas in their solution, they use a for loop. So they have int count is assigned to 0. As long as count is less than max hops, count plus plus. So their version of this, using this count variable, is equivalent to my variable hops, okay, or number of hops taken. So they just called it count. They're just counting how many hops have taken place, and that's the difference between their loop and my loop. Now, there's an additional difference here in that I have a complex condition, whereas they just have this. They just have one Boolean condition to test, which is as long as count is less than the max hops. Okay, that is equivalent to my statement of hops is less than max hops. Where we differ is that I'm only using one chain, so to speak, or one link in a chain of the conditional. I just have an if statement. If the current distance is greater than or equal to the goal distance, return true. Okay? Whereas they have an if-else if. Now, because they're only using this one condition here, count is less than max hops, it is absolutely essential that they have the else if here, okay, to account for the position ever getting negative, all right? Whereas I'm testing that in my loop header. So they're saying position plus equals, same thing as position is assigned to position plus hop distance. That's equivalent to what I have right here in line 28, okay? So far, so good. Next up, they have if the position is greater than or equal to goal distance, okay, return true. So that's precisely equivalent to what I have here in lines 31 through 34. If my curve distance is greater than or equal to goal distance, return true. Else if their position is less than 0. So what I've done, I've encapsulated this piece of information as part of my Boolean expression in my while loop header, okay? And then the count plus plus, I have that, of course, hops plus plus in the loop, which if I didn't include that, then this would just be an infinite loop, and we wouldn't increment the number of hops each time, okay? So it is not required for me to have the else if statement here. And in fact, we just illustrated that by running this simulation, okay? So if you were to write their for loop here, but you didn't have this else if, the else if for if the position is less than 0, return false, then in this particular scenario, it wouldn't have necessarily been true, but it wouldn't have returned false immediately as you're instructed to do so right here, which is if the frog has reached a negative position, then you have to stop and return false immediately. Okay? A couple questions, comments. Do we must return keyword in the end of the loop? I see what you're saying, Jai. So must we return the keyword false? Yes, Jai. Here's why. Okay? So this condition here, right? You're returning true if the position is greater than or equal to goal distance. And then you're returning false if the position at any point in time becomes negative. But since we don't have a variable that's storing, that's storing a value of true or false, we don't have to. You can just say return true or false. We have to return something if these conditions, right, if these conditions are never true. It's possible that neither one of these conditions are ever true, which just means that the maximum number of hops has been met and we still haven't reached our goal distance. So if the maximum number of hops has been met, we've run out of hops to use, and the position is still less than the goal distance, and at no point did the position ever become negative, that just means that the position didn't meet the goal distance given the maximum number of hops. So an example of this would be example 5, right here in the table. So notice in example 5, the frog hopped 5 inches, then 4 inches, 2 inches, 4 inches, 3 inches. yielding a total of 18 inches. So it used up all of the hops that it could, and it still didn't achieve the goal distance of 24 inches, and thus must return false. Okay? So without this returning false here, then you would return nothing, because neither of these conditions ever executed to true, and thus we never got to either one of these down here. Okay? All right, so that now covers everything for part A. Hopefully everybody's feeling pretty good about it. And I'm really glad that we did this question, because the previous two had to do with, the previous two were very, very similar. And that's a good thing, because it shows that from year to year, the questions do have a style, but sometimes they're totally different. And in this case, this frog simulation was completely different to the music downloads and the climbing info classes, totally different. It still hits on, the same skills of being able to use methods from a class where you don't know what the implementation is, but it didn't incorporate the use of any list, and it also incorporated the use of this concept that we haven't used in a while, which is using math.random, generating a random integer, okay? So that wraps up part A. Before we move on to part B, are there still any lingering questions that you have that were not answered in the previous 20 or 30 minutes? All right, if there's a question from part A that you forgot and you remember as I'm talking about part B, feel free to just type it into the chat, and when I return to the chat, I will more than happily answer that question, okay? So on to part B, which says, complete the method simulate below. We did that, okay, part B. Write the run simulations method, which performs a given number of simulations and returns the proportion of simulations in which the frog successfully reached or passed the goal. For example, if the parameter passed to run simulations is 400 and 100 of the 400 simulate method calls return true, then the run simulation method should return 0.25. Complete method run simulations below. Assume that simulate works as specified regardless of what you wrote in part A. And that's the beauty of some of these questions. So even if you got part A totally messed up, but you know what the method for part A is supposed to do, it's supposed to run a simulation and return true or false given these three conditions right here, okay? Given those conditions right here. So we are going to have to make a call to the simulate method to earn full credit. So it says complete the run simulations below. Assume that simulate works as specified regardless of what you wrote in part A. You must, okay? It's very important. I know, we're going to be stressed and we have the time constraints, but it's very important we read everything carefully, okay? You must use the simulate method appropriately to receive full credit, okay? And again, that is there to help you, not to make your life harder. So without using the simulate method, our lives would be much, much more difficult in answering part B, okay? So things to consider here. We basically know that we need a count variable, okay? We're counting how many times the simulate method returns true or false, okay? So if simulate returns true, then you want to increase the count by 1. If it doesn't return true, then don't increase the count. Now, some of you may have thought, okay, that you needed a second count variable to count the total number of simulations that ran, regardless of whether it was true or false. Don't forget, we can utilize this parameter here, num. Num represents the total number of simulations. So it's not necessary to introduce an additional variable to account for the total number of simulations. So if you had something like if simulate is true, then count plus plus, else, sorry, not else, but maybe outside of the if, incrementing a total variable that would increment regardless of whether or not it was true or false. Again, not necessary because num represents the total number of simulations that will be run. All we want to do is count the total number of times the simulate method returns true. And then at the end, we want to return the quotient of the total number of successes and the num, this num parameter here, which will then produce a double, something similar to what we see here. Okay, so let's go ahead and take a look at my solution. So we know the return type is double. So whatever we are returning down here, it better be a double. Okay, it's the easiest way to lose a point. It's the easiest way to gain a point. All right. So I've got two variables that I've introduced here. The first one is called sim round. So what round are we presently in? Okay. The reason we need this variable is we have to account for where we are in the simulation. So if I say in the main method down here, if I say system.out_print sim1.run simulations 400, okay, well, you're going to run the simulation 400 times. When you get to 401, then you are not going to continue to run the simulation, okay? So as long as, and actually we want this just less than, not less than or equal to. So as long as the sim round is less than the num, then we want to continue to run the simulation. Now notice here in my condition, I didn't put equals true, okay? Sort of extraneous code there. You can certainly write if simulate equals true, but there's no need to. Simulate, the method simulate returns true or false. That's what it does. Its return type is Boolean. So it's going by having in line 48 just if simulate, that's like saying if true or if false, okay? So if it's true, then you're going to increase successes by 1. If it's false, you're not going to increase successes by 1. However, regardless of whether or not it's a success or a failure, you want to increase the sim round because that keeps track of how many rounds we've gone through so far, okay? Now, one additional thing I'd like to point out to you is that notice that my success variable has been declared of type double, okay? So I'm going to go ahead and run it, and then we'll take a look at why it's important that this is double, and that it's you could have actually declared it as type int, but then you would have needed to change something in line 54 here, okay? That's another easy way to either get a point or lose a point. So it's actually a pretty straightforward solution. It's not really that convoluted. It's not that complex. Let's go ahead to the main method and test this out. sim1.run simulations 400. And notice it returned 0.715. I'm going to run it again. Just run it a couple times. Make sure you don't get the same number every time. 0.68. But again, depending on the range that you used for your hop distance, this number can vary very drastically, okay? And I'll go ahead and illustrate that in a few minutes as well. So notice here, as I'm just continuing to run it, I'm getting different values each time. That time it happened to be 0.715 again. But again, because of the range that I created for my hop distance method, I'm going to get approximately 70% every time. And again, if I go ahead and change this, so if I change that to, let's say, 31 instead of 41, I go back to the main method and I run it. Let's take a second to observe how the success rate now varies. So now notice I got a much lower number of 0.4825. Run it again. 0.875. The number should be fairly consistent when you use a large sample size. So it makes sense. I'm using the number 400 here, and I'm getting, about 50% every time. If I reduce the number of simulations to, let's say, 50, that number should change. The standard deviation should be larger now that I've reduced the number of simulations. Let's see. So that was 0.44. 0.36. So I am getting more variance now that I've reduced the number of simulations. 50 is still a relatively large number, 0.4. So let's say I reduce the number of simulations to 10. Let's see what happens in terms of the variance we get from, 0.4 again. .3. All right, so we are getting slightly different numbers now that we've reduced the number of simulations. Wow, okay, there we go. Perfect, 0.8, 0.8. So notice, given a very few numbers of simulations, that we got, 30% success rate and then an 80% success rate, given the exact same constraints, the exact same parameters of a goal distance of 24 and a maximum number of hops of 50. So that's a good, really a good representation of how the number of trials or the sample size can impact the outcome of a simulation. So I'm just going to return that number to 400 because that's the one that they used in the problem. I'm just going to go ahead, go back. I can leave this at 31 if I like, and just run it once more. And I'm probably going to get some number around 70%, 0.7 or thereabouts. Oh, interesting. You know what? I guess we got a different number here because I changed this to 31 from 41. So that's right. It was going to be some number, not 70%, but roughly, 45 to 50% each time now that I've reduced that range. And we can see that 0.4725, and we'll just do one last one. 0.4275. Terrific. Okay. All right, let's take a look at your questions. I get like a 25% chance after 400 runs. Well, Matthew, what was your hop distance method is different than mine, right? So depending on the range of integers that's produced by your hop distance method, that has significant implications for the whole rest of the problem and how your simulation will operate. Everyone's simulation is going to be slightly different depending on the integers that are produced by your hop distance method. Let's go. Oh, I see some things here. Okay. We're taking a look at sorry. Okay, let's come back up and take a look at Jia-Yi's code. So Jia-Yi, you have while I is less than the max hops and total is less than the goal distance, and total is greater than 0. And total is greater than 0. Okay. So I represents your hops, and total and total is less than goal distance. Okay. So your while loop header is fine. Then you have your total plus equals hop distance, great. If total is greater than or equal to the goal distance, and I is less than or equal to max hops. Now, here's the thing, Jia-Yi. This line of code right here in your complex condition is extraneous, meaning it's extra. You don't need it because you've already accounted for that in your while loop header, okay? You've already accounted for that here. right? I represents your count, how many hops you've taken. Well, if this isn't true here, then it's not going to be true here either, right? So you don't need to include it a second time. All you need would be if the total is greater than or equal to the goal distance, return true. And then else, oh, I see. You have your condition outside of your loop. You've closed your loop here. You've closed it. You know, Jayi, I think you would have gotten most of the credit here, but I don't think you'd receive full credit, and here's why. Let's say, Jayi, your goal distance was 24 and your max hops was 5, right? What happens if, let's say, the frog hops 20 inches on the first hop, then it hops 10 inches, okay? The way you have, oh, wait a minute, maybe not. I'm looking at your while loop header now. And total is less than the goal distance. So if total is less than the goal distance, so if total exceeds the goal distance, so, okay, you'd actually get more credit than I originally anticipated. One thing you'd want to slightly change here, Jayi, you'd want to have total is less than or equal to goal distance. Because remember, if the total at any point equals the goal distance, then you want to return true, okay? So this should be or equal to, all right? As long as total is, less than or equal to goal distance, then you keep looping through. I see. So I think the way you have this set up is fine. I would just get rid of this here because I believe it's extraneous. However, you didn't increment your count, right? So you're going to get some type of infinite loop. So your I, you didn't do I plus plus anywhere. After this line of code here, you're going to want to put I plus plus, which represents your count of how many hops you took. So after each time you make a call to the hop distance, which simulates the frog hopping, you want to increase I, which for you represents hops, okay, or count. So that you need to increase, you need to put I plus plus after that line of code there, and then I think you're good to go. Would the code still work if you replace the else if conditional with just an if conditional? Great question, Wilson. I'm thinking. So if we just put if, or we'll go to the solution. So here, if we put if. So if position is greater than or equal to goal distance, return true. And then if position, yeah, Wilson, it's still going to work, and I don't think you would get any points taken off. I just think it's good practice. So, and I've been trying to encourage my freshman computer scientists to do the same, because this is a big problem they have with conditionals. A lot of them, they just put if. They have misconceptions about the differences between if, and if, else if, else if, else if, else. I always try to encourage students to use a single conditional chain, right? So if, else if, else if, else, when you are testing something about a variable and that's consistent throughout the conditional chain. So since we're testing something about position here and here, that's how you know you should use an else if, right? There's that classic example of where I've given, where you have grades. So let's say you have, if grade, or rather if average is greater than or equal to 90, print, you earned an A. But if you did that, if you had if, and all the ifs were just if average is greater than or equal to 90, then if average is greater than or equal to 80, if average is greater than or equal to 70, and you do the B, you give a B, print a B for the greater than or equal to 80. See, what's going to happen is whatever the last if is, so let's say you had an average of 95, it's going to print A, B, C, D, okay, or however many conditions you had relative to those letter grades, and that causes a problem where we have a similar example right here where we're testing position, okay? We're testing the position for two different things. It just so happens that these conditions can never both be true, right? So like 95 as an average is greater than or equal to 90, that's true. 95 is also greater than or equal to 80. So that's where when you're using like if, you run into a problem. In this particular case, these two conditions are opposites of each other, right? Since we know that the goal distance has to be an integer greater than 0, then if the position is greater than or equal to the goal distance, then there's no way that the position could ever be less than 0. So since the conditions that you're testing can never be both true at the same time, you can get away with putting if. But since we're testing position in both cases, I would just recommend that you use if, else if, so that you don't fall into a bad habit. That's all. All right, so to give you a very long-winded answer there. Right, so Brittany, you would have been 100% okay to use the if, but again, I just think it's a bad habit that when you're testing a variable in one condition, and then you're testing that same variable right beneath it in another condition, that you use a linked chain like if, else if, rather than if, okay? But again, it wouldn't have made a difference in this particular scenario. And excellent questions to bring up. Great questions to bring up. All right. So that concludes everything from this question. I'm happy that we're really going in depth with these, quality over quantity, although we want to try as many different problems as possible. So don't, if you have the time, I really don't know what everyone's schedules are like. I know that everybody is in a different situation. Some people have multiple siblings sharing one computer, so you have to take turns on when you can get online and do your work. Whereas other people, you may be an only child, you may be, each of you and your siblings have your own individual devices. So everybody has different circumstances, but whatever your circumstances are, just do the best you can. And, don't let me hold you back. I'm really, in some ways, just giving the bare minimum here of what I think is required for us to be successful, because I don't want to give too much and have people feel overwhelmed. So if you're feeling, when I say underwhelmed, like, hey, I kind of wish you would assign more work, just know that there's a million problems for you to work from, that have to do with this topic, as well as the other FRQ that we're going to explore, which will have to do with either arrays or array lists. So you can always go back to APCS Awesome and start to review those chapters about arrays and array lists. Speaking of, since I'm now on that topic, tomorrow will be our midterm. You will be required to answer 2 FRQ-style questions, okay? You don't have to handwrite them. You don't have to type them up in a Word doc or a Google Doc, although you're certainly allowed to if that's what you want to do. You're also welcome to use an IDE of your choice. I will give you double the amount of time that's going to be given to you on the day of the actual exam. So you will have 1 hour and 30 minutes to complete the exam, and you will have an open window throughout the day tomorrow. So, let's say I'll make it available starting at 6 a.m. And I guess I could even make it available at, at midnight, although I wouldn't encourage you to, to do it that late at night. So you'll have all day to do it tomorrow, but you'll only have an hour and a half to do it. So as soon as the hour and a half is up, the assessment will be locked, and you won't be able to, to do anything after that. So make sure that you do everything within the time frame of an hour and a half. I will post it to AP Classroom. Okay, so the problems will be posted to AP Classroom. I already have, so one of them is AP Classroom. The other one is something that I made up that is very similar to the climbing info and music downloads classes. Okay, and then the other question that's in AP Classroom is actually, there are some similarities to the frog simulation. Okay, now again, they openly said on the AP College Board openly says this is an open note, open textbook exam. You can use whatever legitimate resources you have to write your solutions. The reason I don't think they're really all that concerned is because, again, on the day of the exam, you're going to have 25 minutes for one question and 15 minutes for the other. I believe it's 15 minutes for the type of question that we've been presently working on, and then 25 minutes for the array list question. So I feel like they feel like that's, it's a good amount of time, but it's not so much time that you can really start like looking stuff up and scouring the internet, to remind yourself how to use the math.random function, things like that. So if it's little stuff about like, oh, I forgot how to use the index of method, or I forgot how to use the substring method, things like that, hopefully anyway, but those are things you can, get quickly. But yeah, so outside of like, looking up things like that, and using an IDE, which is really, really useful, but it's time consuming. So you're going to have to decide what the best strategy for you is on the day of the exam. I'm giving you double the amount of time needed to answer the 2 questions tomorrow, because I'm going to, I want to allow you to self-assess and use the IDE to determine whether or not, your solution is correct. Is it not correct? Is it almost correct? Something like that. Okay. All right. Any other questions about the midterm tomorrow?